Okay, so let's go over the exam, last week exam. First, that was the first question. You had to analyze these two kinds of glass. Okay, so here we have the SNX and the neutral. And well, first and foremost, those are two high performance glasses. Okay, so I have taken those two examples from a catalog, and I think one of them was a double glazing, the other one was a triple glazing, but they are both what we can consider a high performance glass. The U value is low enough, and then we have different parameters here. And when you're analyzing glasses, we have to look at three different parameters, and you have to give comments on three different parameters. First, the visible light transmittance. Second, the U value. And finally, the solar heat gain coefficient. Mm, we can't have full grade if we don't speak about these three components. Okay, so what about the visible light? The visible light is the amount of natural light that enters the building. So 81, it's always better than 59. Okay, so the more natural light, the better. I would say yes. So the higher this number, the better the glass would be. Okay, so if I had to choose only based on the visible light, this is the second one is better than the first one. What about the solar heat gain coefficient? Well, for the solar heat gain coefficient, is the amount of heat. So this is the amount of visible light, and this is the amount of heat that enters the building. So with this glass, with the second one, it's 0.7, and with the first one, it's 0.2. So 0.7, if we want heat to enter the building, the second option is better. But if we are working in a hot country or in summer, we have to reduce the solar heat gain coefficient. So that would be better. Okay, so basically in warm or hot climates, the first option is better. In a cold climate with a lot of sun hours, the second one is better. Okay, so this is the first comments that I would give. Then what about the U value? The U value, well, the best one, the lower the U value, the better. So the best one is this one, is the first option, fill the air cavity with argon. That gives the lowest U value, 0.18. So this is the best one. What if we select this one, 0.27? Well, 0.27, it's not far from this 0.18, so it's not bad. It has a very high visible transmittance, and it has a very high solar heat gain coefficient. Okay, so I would use this. I told you that I would use this for a cold climate with a lot of sun hours in winter. I would be even more precise now. I would use this for the south facade in a cold climate with a lot of sun hours. Because if we are working with a northern facade, I don't need these solar heat gains because we won't have any sun in the north. Okay. So I would use this first one for Florida or California, and I would use this one for New Hampshire. Let's summarize this. But I would use this one for a southern facade in New Hampshire. For a northern facade in New Hampshire, I would use a triple glazing with a very low solar heat gain coefficient because basically we don't have any sun. Okay. But if you have to analyze glass, you have to analyze these three parameters: the visible light, the U value, and the solar heat gain coefficient. So number two, we had to use that psychrometric chart online, and we have to calculate the wet bulb temperature. So this is in the dry bulb, and this is the relative humidity. Yeah. So let's say that it's 70 and 60. We have to go to this free online chart. This is 70. This is 60. Submit. And the wet bulb temperature is 60.9. So that was the result. Okay. I think this was between 60 and 70. All the, imagine that we can have here 79 and 69. Submit. Okay, so the wet bulb temperature is 71. Yeah, from 60 point something to 70 point something, So that was the answer. Okay, depending on your ID, that we only have to type these two numbers on that website, and that's it. Second, well, this is the U average, but we have to calculate this at the end. We had these two, well, we have this roof with rafters and thermal insulation, and we have all these layers. All the two sections are the same, section 1 and section 2. Section 1 is through the fiberglass, and section 2 is through the rafters, the softwood rafters here. Okay. And now we had to calculate first the R value, and finally the U value, and finally the U average. The only thing, you have to change this EPS. So let's say that this is 2 and 2. Depends on your ID, but let's say that it's 2 and 2. So what, well, if you use the Excel file, we can delete all these. Okay, there you go. This is 2 and 2. Okay, so now we have to go one by one. What is the air ext and the air int? We can find this on lesson 3. You know that we have this table here. We need the roof. Okay, so this is horizontal, heat flow upwards, and this is 2.93 and 1.96. So the first layer here, this is 1 over 2.93, and this was 1 over 1.96. Okay, so this is the R value of this external air layer, and this is the R value of the internal air layer. And we can copy this here. It's the same. And we can copy this here. It's the same. Okay, now what about the wood shingles? Then I have to go lesson 3. Everything's on lesson 3. And I have to go to the roofing materials. Here we have asphalt shingles and wood shingles. So it's 0.97. Okay, so roof shingles, it's 0.97. So here I have to type 0.97 and 0.97. Then I have plywood, 1 inch. So for the plywood on lesson 3, where's plywood? Okay, here. I do have the thermal conductivity of the plywood is 0.8. Okay, so I have to type here the thermal conductivity. It can be 0.8, and thermal conductivity here would be 0.8. And what is the thermal resistance? It's the thickness or the width divided by thermal conductivity, 1.25. So the same thing here. Okay. Now the EPS, 2 inches. Extruded polystyrene, 1 inch is 5. The thermal resistance is 5. So for 2 inches, the thermal resistance would be 10. And that would be 10. Then this layer is different. Here we have the fiberglass, here we have the softwood rafters. Fiberglass, 6 inches of fiberglass. No, this one. Fiberglass 1 inch is 4. So 6 inches is 24. So here I have to type 24. Okay, so in this section, this is the fiberglass. In this section, we have the wood, the softwood rafters. So I have to select softwood here. And softwood, the thermal conductivity is 0.8 here. So here, thermal conductivity is 0.8, and this value is the width divided by thermal conductivity. Then the non-ventilated air cavity, 3 inches. I think one of our, in some of the exercises, I gave you the value 1.5. Well, it's not accurate, but if you had used 1.5, that's fine. But on this lesson, you have this table 2.7, and here we have the thermal resistance of air spaces or air cavities. First, we need to know if it's non-reflective or reflective surfaces. I told you that for reflective surfaces, we had to use either glass or something metallic, can be aluminum or steel, okay? But other than that, everything is non-reflective. So we have brick, concrete, drywall, gypsum, thermal insulation. Those are non-reflective materials. Okay, so here we have to select first cold or winter conditions. If the air cavity is horizontal, the direction of the heat flow is up because we are analyzing a roof. And then we have the 3 inches. It's something between 1/2 and 3.5 inches. Yeah, so it's something between 0.89 and 0.93. 0.9, it's fine, okay. So here we can use 0.9 and 0.9. And finally, we have the drywall. So the drywall 1/2 inch on this, okay, drywall 1/2 inch, it's 0.45. Okay, so now this, I'll do it again. Okay, so this R value is, well, we can select the insert function here. It's sum of all this column, okay? And the U value is 1 over this. So this is the U value of this section, 0.026. And then if I copy this here, that would be 0.045. Okay. So this U value is 0.026. And this one, well, and this one is 0.045. And now we have to calculate the U average. U average is the U value of the thermal insulation, 0.026 times 14, because it's the width of the thermal insulation, times the U value of the rafter, 0.045, times the width of the rafter, 2, divided by 2 plus 14. How much is it? It's 0.026 times 14 plus 0.045 times 2 divided by 16. To 8 units BTU divided by hour feet square Fahrenheit. So this is the U average. Okay, next one. The next one, we have this, we have 6 feet. Some of you have calculated 7 feet, but this example was with 6, 3 and 3. 3 feet with thermal insulation, and the R value of this thermal insulation is 15. And then the area, it was 20 and 40. Some of you, what is the area of the basement? You told me 20 or 20 something times 40 something. This is the floor area of the basement, but we are calculating the area of slices of wall. Okay, so we have to take a slice of 1 foot, and then the area of this, it's the perimeter of this the basement times 1. So if the basement is 20 by 40, the area is 1 foot times 20 plus 20 plus 40 by 40. Okay, so that would be 120 feet square. And then we have to calculate the U value or Q value, the thermal loads. But we have to do it 6 times. Okay, so the area will always be 150. Indoor minus outdoor temperature is always 70 minus -5, because here it's written 70 and -5, okay? And now we have to calculate U values, and there are 6 different U values here. So we need to go over this table. Okay, so in this table, the first 3 feet are insulated, and then from the 3rd to the 6th, they are uninsulated. So if they are uninsulated, we have to take these 3 values, 0.12, 0.10, and 0.08. So that will be Q4. It's 0.12 times this. Q5 is 0.1, and Q6 is 0.08, and this. And what about the first 3 feet? The thermal resistance is 15. So we have to go, if it's 15, we have to select this column. It's 12. So if it's 15, we have to select this column. So the first 3 values are 0.07, 0.06, 0.05. So here it is 0.07 times this. Then Q2, it's 0.06, and then Q3, it's 0.05. Okay, so we have to calculate this, Q1, 2, 3, 4, 5, 6. We have to add everything up, and this is the total Q value. I think it was because depending on the figures X and Y, it was between 4,000 and 5,000. So that was the heating loads through the basement. Okay, but if you have to get used to writing down everything that you have done, because if there's a mistake, if you just type Q total 30,000, how can I know where if it's not correct, if it's not the right answer, it's wrong. And how can I understand, or how can I find out where the mistake is? So there's a few things we have to do here. So first is the area. Second is the U value. And finally, you have to solve all this. So by doing this step by step, I can understand what you have done. If there is a mistake, first, I can help you fix the mistake. And second, I realize where the mistake is, and then I can point it out. But if you just write down the final figure, and if it's wrong, there's nothing I can do. So I can just place a 0, and that's it. Okay, so that's why writing all this, it's important, and writing the formula and then giving values to the formula, that helps me understand what you have done. So next time, make sure that you have all not everything, of course, but at least the relevant steps are there. Okay, for example, here we have to calculate the heating loads through the walls and through the windows. Through the windows, it's quite easy because we have the information, we have the U value of the windows, so that would be 0.2 times the area of the windows. We have 10 windows and 200 and 220 square feet each. So the total is 20 times 10. This is the area of windows. And then indoor minus outdoor temperature. I told you here to use 70 minus 0. Okay, so this is the Q value of the windows. Let's calculate it because I think it will be interesting. This is 0.2 times 200 times 70. Okay, units, BTU hour. What about the walls? Well, first, we have to calculate the U value of the wall. If the R value is 60, then the U value is 1/60 times. What about the area of the wall? Some students have used the total area of the facade, but now we are talking about the wall itself, so we have to subtract the windows. Okay, so imagine that this is 100 times 35, so that would be 100 times 35 minus 200, because we have to subtract the windows, and then times 70 minus 0. How much is this? It's 100 times 35 minus 200 times 70 divided by 60. Okay, so this is 3850 BTU hour. Okay, so with this, I can understand that everything is correct. I can understand that you know what the U value is, the right area for windows and walls, and indoor minus outdoor temperature. Okay, so that would be enough. And units, do not forget units. Finally, the solar heat gains. Okay, so here we have to go step by step. So we have 10 windows, 20 feet square each. The solar heat gain coefficient, it's 0.2. So the area of windows is 200 square feet. Okay, so that's the area of windows. And now we need to use the PV watts, and then we have to use the Excel file to calculate the solar heat gains. So first, we have to go to PV watts. So on PV watts, let me open this again. PV watts. First, location is Keene, New Hampshire. Second, the angle. We are in a vertical wall, so vertical means 90 here. And if it's a south, because we're analyzing south facade in Keene, New Hampshire. Okay, so if it's south, you can click here. So south is 180 degrees. So this is 180. I click here. So the solar radiation in January, it's 3.82. So this is something you have to type here. Solar radiation in January is 3.82. And you can specify here, this is from PV watts. Okay, those are data. The area of windows and solar heat gain coefficient, they are data, so you don't have to specify anything else. And what are the solar heat gains in January? We have to open that Excel file. Okay, so here the solar heat gain coefficient, 0.2. The area of windows, 200. And the solar radiation in January, 3.8. So that's the final number, 48,438. Units, BTU per day. Okay, so those are BTU hours and those are BTU per days. I wasn't asking for the balance between heat gains and heat losses, but if we want to analyze the balance, or the balance, we can use the energy savings. Okay, so here from the window, if we want to know the energy, we have to multiply to 2800 times. If we are working with a day, this is 24 hours. Okay, so that will be 2800 times 24. It's 67,000. 200. And this is BTU per day. Okay, so now we can analyze this energy savings. It's heat losses minus heat gains. but we have to compare the same units. We can't compare BTU per day and BTU per hour. We have to compare BTU per day and BTU per day. So the heat losses are 67,200, and the heat gains are 48,438. Okay, so in this case, we have more losses than gains. Is it bad? Is it wrong? Well, I don't know. Why is that happening? Because the solar heat gain coefficient is very low. If we were using a solar heat gain coefficient of 0.7, probably the solar heat gains would be higher than the heat losses. But that was included in the exam. Okay, so you had to let me know this and these two values, 3,850 and 2,800. So those are the solar heat gains. And finally, we have the ventilation loads. So the ventilation loads, yeah, I've done this before. So the first was without the heat recovery. Sensible and latent heat. What is the formula of sensible heat? It's 1.1 times the CFM. CFM, it's a number of people times 20. So if we have 5 people here, so that would be 5 times 20, this is the CFM, times indoor minus outdoor temperature. So indoor temperature is 70, outdoor temperature 0. Equals. And what about the latent heat? 0.68 times the same, 5 times 20 CFM, times wet bulb, indoor wet bulb minus outdoor wet bulb temperature. When can we find this? Here on this psychrometric chart. So first, what is the indoor wet bulb temperature? If it's 70. And what is the relative humidity? 40. Submit. So the wet bulb temperature is 55.7. So this is 55.7 minus, what is the wet bulb temperature? 0 and 80. Dry bulb 0, relative humidity 80. Submit. So the wet bulb, it's negative 0.6. Minus negative 0.67. Okay, and I think it's interesting if we solve this, we know the numbers are good because we can understand if we are doing things right or wrong. So this is 1.1 times 100 times 70. It's 7,700 BTU hour. And what about this? This is 55.7 plus 0.67 times 100 times 0.68. This is 3,816. No, 33. Okay, and why is interesting looking at this? Because always, especially in winter, sensible heat is always higher than latent heat. Okay, and it's usually it's like double. Okay, so this is 7,000. This is 3,000. Yeah, so it looks correct. Okay, just by looking at this, if the sensible heat is lower than the latent heat, in winter, probably we have done something wrong. Okay, so by looking at this, we have to analyze if we are doing things right or wrong. Okay, so this is without the heat recovery. And what about with the heat recovery? I told you to use this heat recovery. You have to click on that link. And by clicking on that link, we have this recuperator. Here we have to type the indoor conditions. It's 70 and 40. The outdoor conditions is 0 and 80. And then we need to calculate the flow. So the flow, the airflow in feet, cubic feet per hour. The airflow is 5 times 20. So this is 100 cubic feet per minute. Then we have to multiply times 60. So this is 6,000 cubic feet per hour. Okay, so we need 6. Some of you have, I think you have used directly 100, or depending on your ID, on this website, and it's wrong because this is 6,000. And then some of you have used here 10 inches, some of you have used 19. I don't mind, but it's a good thing that you can specify what you have used. So if you are using this heat recovery and you can type here 10 inches, that helps me understand if you, well, what you have done. Okay, I mean, if you have used 10, it's fine. If you have used 19, it's fine as well. I don't mind. But specify what you have used here. And then by using this, the T supply, looking at these details. So the T supply, these are the inlet, indoor inlet, 70 and 40%, outdoor inlet, 0 and 80%. Okay. And then the T supply, in this case, is 63. So this is T supply would be 63. And then the sensible heat, it's 1.1 times 100 times 70 minus 63. And this is BTU hours. $63. Yep. And latent heat is the same as this one. BTU per hour. Okay, so we don't change latent heat. It's only the sensible heat. That's it. Do you have any questions about the exam? No. Okay. Next time, the final exam will be comprehensive. So you will have to calculate the U values, you have to calculate the U average, you will have to know something about glass, basements, heating loads, ventilation. Okay, so there will be more stuff on the final exam, but some of these exercises will be repeated on the final exam. So that's now you don't have to forget what you have learned so far. It's not, okay, this is the midterm. Now I forget everything. I start from, no, 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 no. You have to remember, and even from now until your capstone project, you will have to calculate U values, you will have to calculate the heating loads, and so please don't forget those basic concepts, because if you forget things, you are like kids. So kids don't know anything because they haven't learned anything yet, and they make a lot of mistakes. But as we are learning, and we remember what we have learned, this is what we have to do now. So now it would be beautiful, it would be lovely if we had a tool um, that can include everything. But now you see that we have to, okay, we have to calculate this with the PV watts, and then we have to use this recuperator calculator, and then we have to use this psychrometric chart online. So there, we are using different software now. We are using this Excel file to calculate the U value, and I'm using this Excel file to calculate the solar heat gains. Okay, so there are like 5 or 6 different tools that we're using to calculate or to analyze a building. Well, that's fine. When I was a student, we didn't have this kind of software, and everything has to be done by hand. And it was much more difficult, believe me. So now by using different tools, we can get different results and we can solve different problems. That's fine. But it would be great if we had a tool by which we can calculate everything. So we cannot, we don't have to change, oh, I'm changing this, now I'm using this tool, and I have to close this, and I have to open the other, I have to take this value, and I have to put this value there. Well, that tool exists, okay? And the name of that tool is Revit. Okay, so we have this wonderful tool, Revit. So what can we do with Revit? Revit is what we call building information modeling. Okay, building information modeling, Wikipedia, is a process supported by various tools, technologies, and contracts involving the generation and management of digital representation. Okay, so what is building information modeling? Building information modeling, we need to use software, computer files, but they are all integrated on the same tool. Okay, so well, when I was a student, we had to do everything by hand. When I started designing buildings, I remember that there were different tools. So I had to draw my plans in a tool. Then if I wanted a 3D shot, I have to use another tool. Then if I wanted to calculate thermal loads, I had to use another tool. If I wanted to create the quantity, the bill of quantities, I had to use a different tool. Well, we got by, and we didn't, well, we survived. But now with building information modeling is not something new. It has been there since 2010, I think, or even earlier, because I remember that some of my classmates, they were all studying Allplan. Okay, so Allplan, it's another building information modeling tool. I don't want to log in. Okay, so this is Allplan. Well, there are different companies, and each company are bringing out different software. Allplan, I don't know, but it's not mainstream. You might find someone using Allplan, but now everybody's using Revit. So Revit is the answer to building information modeling that comes from Autodesk. So Autodesk is a giant company. Okay, and we have a lot of software with Autodesk. We have AutoCAD. Yeah, when I was a student, AutoCAD was starting, I remember, but now AutoCAD, well, most of architects my generation, they are using AutoCAD because they don't know how to use Revit. They were old when Revit came out, and they are still using AutoCAD, and they hire young architects because the first, okay, I have received a lot of information in Revit. I don't know how to use Revit, so I need someone to work with Revit files because I don't know, and I'm too old to learn new things. Okay, so this is what people my generation are experiencing now. So you are young now, you will have the opportunity to start working with architects that don't know how to use this this building information modeling software. AutoCAD uses this Fusion 360. This is for industrial engineering, this is for designing, for product design, yeah, for your colleagues in sustainable product design. Probably they will be using Fusion 360, or maybe they are using SolidWorks, which is it's not from Autodesk. But Autodesk is, it's amazing. You have a lot of opportunities here. The good thing of Autodesk is that if you sign in with your Kinestate account, every time you do this, but I have just received this. So my code is, okay. This is my Autodesk account. And if you are from Kingstate College, you are entitled to download all these things. You can download AutoCAD, Revit, 3D Max. I was so young when I was learning 3D Max, and now nobody's using 3D Max anymore. Maya, wow. Fusion. Okay, there are a lot of products. Okay, so especially from architecture, engineering, and so there are a lot of products you can download for free. Okay, or only if you are a Kinestate student or a Kinestate faculty or staff. So make the most of it, because this is not if you sign in with your Kinestate ID, well, your Kinestate email, and then you have to create a password that I think should be the same password that you have for your Kinestate email. But I think you can download everything on your computers. Okay, so you can work on the computer lab, but if you have a good laptop, then you can download any different well, all softwares that you might need from Autodesk. Why Autodesk? I don't know. It's mainstream. Autodesk started with this software, with AutoCAD, and I don't know, 90% of architects were using AutoCAD, and well, so Kinestate decided to have an agreement with Autodesk, because it's when it comes to architectural engineering oriented software, architectural engineering. This is not for design, for graphic design, but it's for architecture and engineering and construction. Okay, so for building science, Autodesk has a lot of opportunities. Anyway, if you download Revit, and I want to be very clear, Revit is not mandatory for this course. If you know how to use Revit, that's fine. By the way, any one of you has taken CAD 2 so far? None of you? I don't believe it. Ethan, are you there? Is somebody there? Oh, yes. Did you take CAD 2?
Wait, sorry. Say that again. My computer acted up.
Yeah, no, Ethan, you took SketchUp last year. I know that. Did you?
Yeah.
Yeah.
Yeah, I took SketchUp last year.
Okay. So you are where are you, by the way? So you are Alan. Okay.
Yeah,
So
I'm
you took
Alan.
SketchUp. Did you take CAD 2 or you took only CAD 1?
I took CAD. I took CAD 2 also.
Okay, so you know how to use Revit,
Yes.
kind of. Do
Yeah,
you know how
kind
to
of.
change materials in Revit or?
Uh, yeah, to change materials in Revit, don't
Mhm.
you go to I think it's either insert or manage?
Insert or manage? Oh, yes. So in manage, you can load materials. No,
Yeah.
but I mean, did you learn how to calculate the U value or the R value in Revit?
Oh no, we did not learn that.
Okay. No, that makes sense because CAD 2 it's for modeling. Okay,
Yeah.
but now, but look at this. I'm sure that you can select a wall. And have you used this edit type command or not yet?
Yes, we have.
Okay, so you have used this. So by doing this, well, here we have the a drawing of the wall that we are designing. Okay, but if you edit this, the structure here, you can select different layers of Revit. Okay, so here this is brick, but if we click here, then we can, if we want to select concrete masonry units, I can type here concrete. So I have a concrete masonry unit here. And if I look at the thermal properties, I have the thermal conductivity, specific heat, density, all the properties that where I'm using international units because this is a project of my own. Okay. And so I'm using international units, but you can use British units as well. But here you have thermal conductivity of all the materials you might need. So if you need brick, so here we have the thermal conductivity. You have thermal insulation materials, thermal. Well, we have rigid insulation. This rigid insulation, it's EPS, so it's the extruded polystyrene. So here you have the thermal conductivity. Okay, so there's a library here, and if you don't find the material that you are looking for, you can create your new material here. Okay, so you can put the name of you, I don't know, fiberglass. Fiberglass. So if you know um, the thermal properties of fiberglass, then you can add them here. Okay, so there are a lot of things we can do with Revit. And the good thing is that when we are working with that, we can change here the thickness. This is brick, so let's say that we have 4 inches. And here you see that we have the thermal resistance. Okay, so this thermal resistance is 4 point something. I told you this is international units. So if you want to see how that changes, I can, do I have the thermal insulation here? Okay, I have the rigid insulation here. So I'm increasing the thickness. So that will change. Now it was 4.2. And if I do this, now it's 5.6. Okay, so I have changed the thermal resistance. And if I look at this, I have the heat transfer coefficient. I have the U value here as well. Okay. And I can do this with walls. I can do this with roofs. Okay, so I can edit type here. And by editing type, well, I have here the heat transfer coefficient. I can edit this. I can change the, or I can insert Category, so I can say that this is the rigid insulation. Okay, I can change the thickness. And by doing this, I change the U value. Okay, so we don't have to calculate. I don't need the Excel file to calculate this. What about the glass? So for the glass, if I select this and I edit type, I can select here. You see that by default, well, by default, in this project, I have a low emissivity triple glazing and the solar heat gain coefficient, it's 0.2. But I can change that, okay? So I have a different solar heat gain coefficient. And if I change this, I get the visible light transmittance, 0.68, the solar heat gain coefficient, 0.62, the thermal resistance, the U value. So everything's here. Okay, so I have a lot of options. Here I have the triple glass, I have single glass, double glazing, everything here. Okay, so I have a default library of materials, and I have plenty of options here. So I can design my own, my own wall, the floor, the roof. But we can do even more. If we click analyze here, and we click heating and cooling loads. So first we have to design spaces. I have to, if you're interested in that, I have to teach you how to design those spaces, okay? But if we click calculate, you have a load report. So here you have the project summary. Here we have the cooling, the heating loads, and this is the summary of the building, but we can break down heating loads in walls, windows, door, roof, ventilation. Okay, so basically what we have done so far. This is the cooling. In cooling, we have more components, but for heating, we have walls, window, door, roof. We don't have any skylights or partitions. We have infiltration and ventilation. So this is about, we haven't talked about infiltration, but we have talked about ventilation. And if we go space by space, so here we have a summary. So we have the total heating loads of that space. So we can analyze not the whole building, but we can analyze room by room. We have done this in the first assignment. We have analyzed different floors, okay? So we can do that in Revit by defining different spaces. So have everything, space 13. Okay, so here we can calculate everything, and we have the area, the wall area, the roof area, the window area. So we don't have to subtract the area of the facade. We don't have to subtract the area of windows. So everything is there. So that's why we call this building information modeling, because by modeling an object, we have a lot of information here. So we don't have to model these, and then we have to take the measurements, and we have to go to calculate the thermal loads, and then we have to calculate the solar heat gains. Everything's there. Everything is on the everything is in this model. But what I like the most about Revit is the solar analysis, okay? Because here we can click sun path on, okay? So by doing this, I can analyze the sun, where the sun is with respect to my house. So first we need the orientation. So you can see we have this compass here. It's the north, east, west, south. So this is the roof plan of the building. And I can change the date here. We tend to think that the sun rises in the east and sets in the west, but that happens only twice a year. It happens on September the 21st, so it happened a few weeks ago. So we had this in which the sun is rising right in the east and is setting right in the west, and it happens in March. Okay, but other than that, if we analyze what goes on in June the 6th, no, in June the 21st, sorry. So you see that the sun rises here. This is not the east, this is the northeast, and it sets here in the northwest. Okay, so this is important to understand. And what about in December? So in December, the sun rises here in the southeast and sets here in the southwest. And what about the height? Okay, so look at in December, the height of the sun, or the sun, it's very low in the horizon. But in June, it's very high. Okay, so this is very useful because now we have to go farther. We have to design with passive measures. We are not talking about active measures here. We're not talking about any device. We're just talking about the amount of glass that we have here and the overhangs, and we're designing the roof. So what do we want? In winter, we want a lot of solar heat gains, but in summer, we don't want any solar heat gains. Okay, so we can activate shadows here. And this is very important because if you can see here, all my windows, they are large windows, but my windows are, this overhang is casting shadows, so I don't have any sun here. And I don't have any sun from early in the morning until the afternoon. Okay, so I don't have sun. But what happens in winter? If we analyze December, so in December we have a lot of solar gains, especially in the morning and in the afternoon. Okay, so we have a lot of solar gains. Why? Because the sun, it's almost horizontal, so this overhang doesn't affect this shadow. Okay, so this is what we call a solar analysis of a house. This is a passive solar analysis because but this is what we want, and this is very effective because we have solar gains in winter and we don't have any solar gains in summer. In summer, the overhang casts shadows on the glass so that none of this sun enters the building. Okay, so these are good design decisions, and we have dimensioned these overhangs wisely. If we didn't have this overhang, for example, if we didn't have this, if we had just a roof like this, okay, so in summer, look at this, there are a lot of solar heat gains through this window in summer. But by designing this overhang, we don't have any solar heat gain here. So those are design decisions. I mean, we don't have to, we're not using any device here, any movable louvers or blinds or whatever. No, it's just designing something that it's fixed, but it works. It works in summer and it works in winter. And then we have to select the right glass for sure. Yes, we have to select the right glass. And we have to select the right amount of thermal insulation here. But there is more than with passive measures. It's not only about selecting the right window or increasing the thickness of thermal insulation. There is more, and it's about design. It's about the solar analysis of the building. We can do this with Revit, we can do this with SketchUp, okay? But I think it's great. And the good thing in Revit is that once we have modeled the building, we can have the heating load analysis, we can have the solar analysis, we can even analyze we have an option to analyze the PV, the photovoltaic panels, and the energy that they are generating. So once we have modeled this with Revit, there are a lot of options with the same file. We don't have to change software. So on on Wednesday, I want you to show me your Design One project, and well, because we will have to run all these analyses. And if you are not taking Design One, I will provide you with a project that you will have to analyze first, and then you will have to modify. So it will be like a kind of energy retrofitting for this. So you will have to change the project. Okay, so it's because I'm giving you a project that it's not a zero energy building at all. That you will have to modify to turn it into something that can be a zero energy building. Okay, but we are not using Revit. We are going to use an Excel file, but I want to show you what we can do with an Excel file. We can do a lot of things. Okay, so it's not a perfect tool. It's not Revit. We cannot model a building here in Excel. But once we have, we know how it works, there are a lot of things we can make with an Excel file. So this is what I have done and I will share this with you later, this Excel file. So what is this? This is the wall. So you know how to do that. We have different layers, thermal conductivity, the width, thermal resistance, and the U value. And then if here you type the area of the wall, here you have the heating load through the wall, okay, with the U value. And the area of the wall, we can find the total thermal load through the wall. I have included the basement here. Okay, so on the basement, you remember that table? It's this one. Okay, but it was only until, so it was useful only for 7 feet. So I have included here 9 feet. I think more than 9 feet in a basement. It's very unlikely. So here we have the 4 columns, the uninsulated one, and different R values. And what do you have to do here? Well, if we have an uninsulated wall, only 6 feet, so you have to select these values and copy them here. Okay. Then the area of the basement is the, well, is the perimeter and times 1. So it's the area of the basement. You have to type here the area of the basement. And then the thermal load of the basement takes into account all these columns. Okay, so it's U1 times the area times indoor minus outdoor, U2 times the area times indoor minus outdoor. Okay, so you have this value here, the total value of the thermal load through the basement. So let's do something that we know that's going to be bad with only 4 inches of thermal insulation with an uninsulated basement. Here we have the roof. Okay, so for the roof, we have the roof through the thermal insulation with 14 inches, the roof rafters with 2 inches. So you can modify this here. You have the U value through the thermal insulation, the U value through the rafter, the area of the roof. So you have to type here the area of the roof. And here you have the thermal load. So the thermal load is, well, first we have the U average, sorry. So the U average is the U value through the thermal insulation times 14 plus the U value through the rafter times 2 divided by 2 plus 14. Okay, so with this we calculate the U average. You have to type the area of the roof, and this is the thermal load. It's the U average times area times indoor minus outdoor temperature. Well, this is new, and what I have done is to include this Excel file here. Okay, so now you don't have to use it. Here we have the solar heat gain coefficient in the area of windows. So here you have the U value of the window, the solar heat gain coefficient, and the area of the window as well. And this is for the north, for the south, the east, and west. So these values are taken from PV watts. This is for Keene, New Hampshire. Okay, so if we are working with the PV watts, in Keene, New Hampshire, with vertical windows in the south. Okay, so this is 3.8, 4.2, 3.8 on this website. On the south elevation, it's 3.8, 4.8, 3.9. Well, it's rounded up. Okay, but I have copied the values that we take from PV watts in the south elevation, north elevation, east, and west. Okay, so by changing this, let's say that this is 0.5. We are not using a good window. It's 0.5. And the solar heat gain coefficient, well, let's say 0.5, 0.7 as well. Okay. We only have to select the area of the window and the solar heat gain coefficient of each elevation. And we can calculate ventilation loads. So for the ventilation loads, for the sensible heat, here you have number of people and CFM per people. It's always 20, but here we can change the number of people, 20. We have sensible and latent heat. And well, here I have included the overall energy heat recovery efficiency. If you remember this, okay, so this is 90, 89, 92, 90. So the effectiveness of this energy of this heat recovery, it's around 90 for the sensible heat. So we can type 90 here, okay. But let's if we type 0, means that we don't have any energy heat recovery. Okay, so now we can look at this. So these are the peak thermal loads. So by analyzing this, well, I can see that the ventilation load is, and then the windows, and then the basement. Okay, so now I can start fixing things because this is my thermal performance, the thermal performance of my building, but without any improvements. So I have an uninsulated basement. I have bad windows with a very with a high U value, and I don't have a heat recovery. Okay, so what can I do? I mean, can I do something for the roof? I think the roof is good enough. Then the walls, yeah, maybe I can do something for the walls. But if I had to address an issue here, I will start addressing the ventilation, the windows, and the basement. So let's do the basement. So on the basement, we didn't have any thermal insulation. Okay, so it's an uninsulated. Okay, so let's use the maximum insulation of the basement. So I can copy and paste it here. And now the thermal loads of the basement, okay, they are even below than the thermal loads through the walls. Okay, so placing thermal insulation in the basement, it makes a difference. Let's do that. What about the ventilation? What can I do? I can use a heat recovery. This is without the heat recovery. What if I have a 90% heat recovery here? Okay, I can drop the energy consumption of this. And what about the windows? What if I change these windows? It's 0.5. What if I use one of these windows with 0.18? Okay, I can use this triple glazing. U value it's 0.18. So let's do it. 0.18, 0.18. There you go. Now everything has been reduced, and now the maximum heating load is through the wall. So I have solved the basement issues. I have used the heat recovery. I have reduced the U value of the window. So now the maximum thing is on the walls. Can I do something with the walls? So let's look at the walls. And for the walls, I have only 2 layers of glass wool. Glass wool is like fiberglass. So this is the thermal insulation, but there is only 4 inches. What if I use 10 inches here? Okay, so now the U value or the thermal loads through the walls have dropped. Can I do anything else? Well, probably. But now I have used heat recovery. I have used triple glass. I have used thermal insulation around the basement. And then I have increased the thermal insulation of the walls. Well, it's not bad. It's much better than a couple of minutes ago. Okay, so I think this Excel file, it's useful to check everything that we have done so far. And you don't have to do it by hand or using different software. No, you can use this Excel file, and just by changing the U value of the window, by changing the effectiveness of the heat recovery, and by increasing the thickness of thermal insulation of walls and roofs and basement, there are a lot of things we can do. And now comparing the before and after these active measures, it's something quite easy.